G'day everybody and welcome back. So what is horsepower and what is torque? Well, put simply, horsepower is how fast you're going to hit a fence and torque is how far you're going to drag that fence with you. Welcome to Andy's Motorcycle Obsessions. So we want to put basket case onto a dynamometer, but before we go and do that, I think it's important to understand what horsepower is, where it comes from, how it's derived, and what its relationship is to torque and RPM, and what we actually are looking for on a dyno, and what we're trying to achieve. So for that, it's over to the newly installed Andy's Motorcycle Obsessions Engineering Whiteboard. And here it is. So it's the late 1700s. James Watt has now refined his steam engine to the point where it's commercially viable, and he's got this technology on his hands that could potentially change the world in terms of manufacturing. But he had to sell it, and like any new technology, you've got to be able to convince your customers that what you're peddling is going to be as efficient, or if not more, and makes sense from a business perspective than the existing technology, which was the horse. So it made sense to draw that comparison. So Watt did a series of experiments, and he came up with the definition that essentially 1 horsepower is a measure of work done in 1 minute divided by 33,000. 1 horse, according to Watt, could lift 33,000 pounds over a distance of 1 foot in a time of 1 minute. That is 1 horsepower. But of course, an engine works rotationally, so we have to translate the work done in a circle to that of what is done in a straight line, as in Watts' original example. And the way we do that is that we use torque. Torque is a measure of an engine's twisting power, its twisting ability. And torque is measured as force times the radius. So the radius of your crankshaft, or half of the length of your stroke, is R, and force is the mean average of the cylinder pressure that's generated during the power stroke. We have to introduce pi because we're working in a circle. So to find out our horsepower equation, it is R, radius, times 2 times 3.142, which is pi, times force, the cylinder pressure, multiplied by the RPM, because it's a time factor. And then the whole lot is divided by the constant that James Watt derived, which is 33,000. Well, that's a fairly complicated formula. We can simplify things because we know that force times radius is equal to torque, so we can get rid of the R and the F and just bring in torque, and the formula looks like this. Horsepower equals 2 times pi times torque times RPM divided by 33,000. So that's a little bit easier to use, but we can simplify it even further, and we can eliminate the 2 times pi. And we do that by dividing it into the 33,000. Remove from the top line, divide it into the bottom line, and we end up with this. Horsepower equals torque times RPM divided by 5,252. And that is the universal formula for horsepower. Okay, let's have a look at a practical example and how it's applied. We have an engine here that is rated at 200 foot-pound by 1,000 RPM, and I've only done this purely for the simplicity of the math. When you look up an engine spec for a vehicle, it will usually have a horsepower rating at a given RPM, and that is what your horsepower is derived from. So 200 foot-pounds at 1,000 RPM means that this engine will, at this pulley doing 1,000 RPM, will lift a 200 pound weight in 1 minute 1,000 feet, assuming that the circumference of that rear sprocket there is 1 foot and the drive is 1:1. So we've got a 1:1 drive, 1 foot circumference here, 1 foot circumference there. The motor's doing 1,000 RPM. We know it's got 200 foot-pounds of torque. It will lift that 200-pound weight 1,000 feet in that minute. So in order to determine what the horsepower is, we need to apply the horsepower equation. So it's 200 foot-pound times 1,000 RPM divided by 52. And I have worked this out already on my calculator. I know that the horsepower for this motor setup is 38 horsepower. But what if we wanted to lift a heavier weight? What if we want to lift 400 pounds? What's going to happen here? We're going to exceed the torque limits of our motor, which is only 200 foot-pound. So the motor will stall. It's like trying to take off in 5th gear. We exceeded the limits, motor stops. So we've got two options. We can either go back out and buy another motor that's rated at 400 foot-pounds, or we can introduce gearing. So let's have a look at the gearing. So what we've effectively done here is we've doubled the ratio from 1:1 to 2:1. So we still have 1 foot of circumference here, but we now have 2 feet of circumference there. And what we've done effectively now is we've doubled the torque. So instead of producing 200 foot-pound of torque here, we're now producing 400 foot-pound of torque. But when you change ratios, you increase your torque, you proportionally decrease your RPMs. So now we're only doing 500 RPMs here. We're still doing 1,000 RPM there, but we're only doing 500 RPM at the driven end. So to lift our 400 pounds, it will do it now, but it's going to take twice as long. It's going to take 2 minutes at 2:1. But let's have a look at what that does to our horsepower figure. So we plug it in, we've now got 400 foot-pound multiplied by 500 RPM divided by 52. Surprise, surprise, 400 times 500 is 200,000. 200 by 1,000 is 200,000. So the top line remains the same, the bottom line remains the same. Divide one into the other, you end up with 38 horsepower. So you're not going to change your horsepower of your engine by changing your final drive. You can change chains and sprockets, wheel diameters, do whatever you like. The engine's going to have the same horsepower. Yes, you'll change the torque. And that's why you have a gearbox. So first gear, the engine revs really hard, but and develops a heap of torque, but you're not going to go very fast because you don't have the RPMs at the back wheel. And then the further up through the gearbox you go, the more the torque goes down and the RPM goes up at the back wheel and gives you that drive. So I hope that dispels any myth about horsepower and final drive ratios. Want it on? Hey! Happy days, it started first time. what's the wash up? You know, what did we gain out of that? Well, I got some really useful information. First thing we did was rebalance the carbs, because remember, I haven't had them balanced since we did the top end rebuild. So we threw it on the slab. Red's got a very advanced computer analyzer for the carburetor balancing, and he was able to get them very well balanced. Or as good as you can expect. They're very finicky, these race carbs. The other thing that he said to me, it's nearly a waste of time putting it on the dyno because I've got a tank full of 98 octane and that's what I've always run. And he suggested to me that it burns too slow and that the piston's already past that that point in the power stroke where you're not getting the most out of your combustion. So I'm going to go back to 91. He said that you'll pick up a couple of horsepower, 2-3 horsepower, just by changing the fuel. So I'll take that advice on board. The other interesting thing was that we made more horsepower at 3/4 throttle than we did at full throttle, and that's because the carburetors are probably a little bit too big. Maybe a 34mm carb would give me a better spread at full throttle. But this isn't a drag bike and we don't go racing really, so for street use it's fine. Horsepower numbers, at 3/4 throttle we made 79.8 horsepower, and at full throttle we made 79.5 horsepower. One of the things that we looked at on the air fuel ratios was that while the jetting is good, pilot jet and main jet sizes are fine, needle position seems to be fine, but the shape of the needle could do with some refinement if I wanted to be pedantic. There's a bit of a discrepancy there between from the bottom of the needle movement to the top of the needle movement, so it could be a little bit more linear. So yeah, I think for what it is, I'm happy. Am I disappointed with the horsepower figure? Yeah, maybe I am a little bit, but Red went on to explain to me that one, you're going to get more than 80 horsepower just by swapping your fuel over. And the other thing is that a lot of the horsepower figures that you see out there, big number ones, come from the Dynajet dynamometers. And they have a fudge factor in them. And that dates back to the mid-80s when they were developing dynamometers. And the people developing the Dynajet couldn't get the derived horsepower to match the accepted horsepower. So I think it was an 85 Yamaha that was the highest rated horsepower bike in the world at the time, 140 horsepower claimed. Best they could manage on a dyno was 90. So they put a fudge figure in, and basically from that point on, that was the datum, and all other bikes were measured at that. So that fudge factor will throw your horsepower reading on the high side by 17 odd %. So no, I'm not happy. This machine was built. I'm not unhappy. This machine was built in Australia. It's adjusted horsepower for atmospheric conditions and temperatures, etc. So the real world rear wheel horsepower number is what you see. And I know that my mate Dutchie's Z1100, they put that on the dynamometer, and that's a beefy bike. It's fuel injected. It's big bore kit out of 1502, and on the same dyno he got 99.8 horsepower. So yeah, no, I'm not unhappy. So this is accurate, and he said to me it is what you would expect to see from this size engine in this configuration, and he said that he's not at all unhappy with the horsepower result. So I know how it rides, I know how it feels, and that's all that matters to me. So where to from here? Well, I think that I'm just going to continue to ride it. I'll change the fuel and just enjoy the bloody bike. But certainly I lucked out because the carburetor setup was really good. But if you're trying to tune for horsepower, it is an essential tool, the dynamometer. So for me now, I guess if I want to improve, I could think about going to a big bore kit, which I am thinking about doing, or maybe doing some advanced cylinder head work, so some porting and valve work to try and get that get the head to flow better. But I think we should wrap that up now. I hope you enjoyed it, because I certainly did. It was a lot of fun, and it was good to see the old girl, stretch its legs up to 200 kilometres an hour, even if it was on a rolling road. And don't forget to like, subscribe and comment, and I'll catch you next time on the Indy's Motorcycle Obsessions. Bye for now.